All right, section 10.5, we're going to talk about lines and planes in 3 space. So I want to recall with you, you've seen in 2 dimensions that a line is determined by 2 points. You fix 2 points and there's a unique line between those 2 points. Another way, though, to think about a line is if you have a 1 point plus a direction. And so you have a point and you have a direction, then you have a unique line that goes through that point with any given direction. And so in 2 space, we think about the direction as the slope. In 3 space, though, we're going to think about the direction as a vector. So the point is, the same thing is true in 3 space. If you have 2 points in 3 space, there's a unique line through those points. And if you have a point plus a direction vector, then there is a unique line through that point that's parallel to your direction vector v. So let me see if I can sketch this out with you. I'm going to come up with a formula together. So let's consider the line passing through some arbitrary point, and then it goes in the same direction as this random vector v. We're going to call v the dimension vector. So let's do pink, and let's make our line a little bit bigger. So we're going to do something like this. Okay, there's my line, and I want to do, we'll say that this point is the point P naught, because P naught lies on the line. V is parallel to the line, so V we could think about as floating out here somewhere, but I'm actually going to drop V on the line itself. We're going to put it right there. And then what I want to do is I want to pick another point on the line somewhere out here. I'm going to call this point P. And I'm going to think about P as the point X, Y, Z. We already said P naught was the point X naught, Y naught, Z naught. And now, to help us really see what's going on, I want to imagine way down there somewhere the origin. And I'm going to think about, let me find a color that I like. Let's do this color. We're going to think about some lines, some vectors starting at the origin and shooting out to my point. So I've got this vector, and then I've got this vector. And so I'm going to think about these actually as vectors now. Are you with me? So this vector right here that I'm working on is going to be R naught. And by the way, you can write down the component form of R naught. R naught is just the vector X naught, Y naught, Z naught. Anytime you pick a point, there's an associated vector in standard position. This vector, you know what, let's erase this, and I bet I can make it look a little bit better here. There we go. So we're going to have R naught. We'll just draw the line out here, actually. R naught is going to go there. There's R naught, and then we'll call this vector R. And so again, R is just the vector who's in standard position and whose head is X, Y, Z. And so now I want you to think about what it means for this point P to be on the line. I've got a vector here, and I've got a vector here, and I'm interested in this vector in between them. You tell me what it is in terms of R naught and R. Hopefully you know it's exactly R minus R naught, right? That's this vector. And so you can see now, let's write it together. The P lies on the line if and only if the vector R minus R naught is parallel to the vector V. Here's my vector V. Here's my direction vector V. And so R minus R naught needs to be parallel to V. Now let's ask ourselves, what does it mean for R minus R naught to be parallel to V? Well, it means it needs to be a constant multiple. So we could say this happens if and only if R minus R naught is equal to some multiple times V, some constant times V. And that works. I'm going to use a different letter. I want to use the letter T, and I'll show you why in a minute. And so now I can write R equals R naught plus TV. And that is the first equation of a line that we come up. And what I want you to realize is that as you let T vary, you move R. You move the tip of R. So ultimately, R controls this point X, Y, Z. So for example, if T equals 1, then you're sitting right here at the end of V. If t equals 2, you're going to go out 2 multiples of v out to there. If t equals a half, then p is going to be right there. If t equals negative a half, then p is going to be right there. So by controlling t, you pick up every possible point on this line. You can hit them all. So that is what's called the vector equation of this line. So I want to write down a little bit more with you. So let's actually write out what this is. So my r here is, in vector form, is this arbitrary point x, y, z. That's what r is. My r naught is this fixed point that's on my line, x naught, y naught, z naught, plus t times, and my v is a direction vector a, b, c. And what I want you to realize is that nothing is changing on the right-hand side except for t. This is fixed. This is a fixed point. This is fixed. It's a fixed vector. And so as you change t, you change the output over here. It all comes down to t. So I've written that out for us. Since this equation only depends on t, everything else is stable, then we use the following notation. And so here it is. We'll often actually think about this side as not just r, but r of t. It's a function of t. We'll talk about this more a little later in the chapter. And so my r naught, again, is a point, but I'm thinking of it as a vector on my line, and v is the direction vector of the line. And so if we let's take this equation right here, and let's actually copy it and drop it in here. And I want us now to realize that if we want to, we can we can combine these vectors together, and we can say, all right, this is x, y, z, and I get the vector x naught plus t times a, comma y naught plus t times b, comma z naught plus t times c. And now we can relate the components. We can say, okay, look, the first component x has to equal this component. And so I get x equals x naught plus t times a, y equals y naught plus t times b, and z equals z naught plus t times c. And by the way, I should mention, these are called the parametric equations of the line. So we have the vector form, or the vector equation. I think I'll change this to vector equation just because I think your book is going to say it that way. You have the vector equation of the line, which is r of t is r naught plus tv. You have the parametric equations of the line. They're saying the same thing, by the way, same thing. And finally, I want to point out to you that if a and b and c, if none of them are 0, then you can actually solve for t in each equation. So for example, if I solve for t here, I'm going to move the x naught over and then divide by a. And so I get t equals x minus x naught over a. Do the same thing here, move the y naught over, divide by b, and that's also equal to t. And the same thing here, divide by c, and that's also equal to t. Since each of these is equal to t, then they're all equal to each other as well. And so these are called the symmetric equations of our line. And so you'll be asked to find the vector equation, the parametric equation, and the symmetric equations as well. I'll simply mention that there are cases when one or more of these A's, B's, and C's could be 0. They are 0. And so I'll simply refer you to the book in those cases. We won't mess with that too much, but you can actually write down the symmetric equations in those cases as well. So let's end the video here. In the next video, let's work out an example together and see how this actually goes.